Board, and it's my pleasure today to introduce Professor Michael Kleeman, who's with the Department of Civil and Environmental Engineering at the University of California, Davis. The great progress we've been able to make in California on reducing air pollution is in large part due to the strong scientific community we have here focused on understanding the emissions, transport, transformation, exposure, health effects, and control of air pollution. And Mike's been a stalwart in this regard, beginning with his PhD at Caltech under the late great Professor Glenn Cass, where he studied source apportionment of PM. And he's continued that vein of research through his 15 years at UC Davis, and taking advantage of increasing improvements in computer power by developing increasingly complex computer models and then doing more sophisticated measurements that take advantage of the latest instrumentations. And so Mike and other students of Glenn Cass are kind of unique in that they're both measurement and modeling experts, and we certainly benefited from all the research that they've done. Mike himself has produced 90 peer-reviewed publications ranging from the effects of agricultural sources on ozone to the effect of climate on PM and pretty much everything in between. And today he'll be talking on his latest ARB funded project looking at PM contributions from light duty vehicles. Please join me in welcoming Mike today.
Okay. Thanks, Bart, and thanks for everyone for coming. We've had a lot of really great projects with ARB over the years, and I think this is another example of a successful partnership of bringing a lot of interesting resources and cutting-edge stuff together to study a compelling, interesting problem. In this case, understanding the volatility of the primary emissions from motor vehicles. I want to start by acknowledging all the great team members that we had on this project. Things succeeded pretty well, as I'll show you in the publication list later on, but we had a number of very hardworking students and postdocs and other professors involved in this. Toshi Kuwayama is a PhD student just graduating now that worked with me. Chris Kappa is a professor at Davis. Sonia Collier is a postdoc working with Chi Zhang on the AMS side. Isabel Faria was a postdoc, and Sarah Forestieri is a graduate student. And all of them came together and provided a unique dimension to this. And so it was a really successful effort. We also had another successful collaboration with the team down in El Monte. Every time we go down there, it turns into very long days, sometimes very long nights as well. And the team down there is just amazing in their commitment to getting some science done. They all rally around there and they all work really, really hard. And so I want to give them a lot of credit as well. And then various people have contributed to this as well. Peter Green and Chris Jacober as well, involved in similar past projects, helping out to make this all a success. So I'm going to focus on results that have been published or are in the process of being published through this project. There's 7 or 8 papers here. I'm going to focus mostly on the results from paper number 4, but I'm going to touch on elements of some other papers as well. I just can't stuff it all into a 1-hour seminar and do justice to it. And some of these things, obviously, my colleagues would be better suited to give the seminar on than I would. So I'll defer to them on questions about the details of the AMS, although I will touch on some of the interesting issues that came up with that technique as we go through this. So just by way of some framing this, and I think everybody here is pretty tuned into this, but maybe some folks on the net would benefit from a little background. There's been work in the past decade looking at the volatility of primary organic aerosol. And the idea is that primary organic aerosol is not rocks. It's actually semi-volatile material, perhaps. And especially it's semi-volatile material if you measure it in very high concentrations, you push more of that semi-volatile stuff into the condensed phase. And back in the 90s, we didn't really recognize this about organic aerosols. Glenn's wisdom and kind of genius in the whole thing in developing the dilution sampler was that you try to get things down to ambient concentrations so that you can measure stuff with the normal ambient sampling equipment. And that's actually something that has served us very well throughout many, many years of studies is don't study a system at industrial concentrations and somehow think you're smart enough to project what it means into the ambient. Try to get it close to the ambient as you can, and then measure it with the same techniques that you use for ambient, and you'll skip a lot of complexity out of this. And Glenn was very wise when he had designed the dilution sampler to do that. There's been a lot of measurements by other groups over the years that measured things from emission sources at milligram concentrations or hundreds of micrograms concentrations, things that are completely unrealistic. And when you do that, you can definitely see some of this behavior where things behave very semi-volatile. If you increase the dilution factor, you add a little bit more clean air in with it, you'll see that particle phase start to evaporate. And that definitely happens, and these measurements showed that. The theory was, though, that, well, maybe all of this happens. And so you can see on the lower part of this graph the concentration going from milligrams down to 1 microgram per cubic meter finally. And there was a lot of benefit to seeing the semi-volatile nature of this at high concentrations and coming up with a theory to explain it, but then they extrapolated down to the low end. They extrapolated. We didn't have very many measurements below 30 micrograms, which is typical ambient, and so you push that line, and that line goes way, way down there. And so the question became, well, maybe all primary organic aerosol is semi-volatile, and you're just wasting your time measuring primary organic aerosol, period, and the game is all in the secondary phase, not in the primary phase. And we didn't think that was realistic. You can actually see the data kind of flattening out, and we had made a lot of measurements, which I'll touch on as well, that didn't seem to really go along with that theory, and so that was the motivation for this project. So in previous work in 2002 and 3, we were working at El Monte under ARB sponsorship, measuring the emissions from motor vehicles. Lots of people, even in this room, were kind of involved either directly or indirectly with that. And we thought that we could actually chemically speciate a significant fraction of the organic aerosol. We were working at pretty low concentrations, and we thought that we could account for the chemical speciation of roughly 30% of that organic aerosol. And when we looked at the chemical composition, it was a lot of oxygenated material. Aliphatic aldehydes, dicarbonyls, some aromatics back then, but not as many. We looked at the partitioning of that and trying to think of, would it follow that absorption model where you expect it to evaporate? And what we found is that it just didn't seem to follow the absorption model, period, let alone whether you worry about whether it would evaporate or not. It shouldn't have been in the condensed phase in the first place. And that suggested to us very strongly that absorption actually at these low concentrations doesn't explain what's going on. Perhaps adsorption, like a surface bonding process or some other chemical speciation process was going on. Our best explanation for this result, and these light carbonyls being in the condensed phase, was that they don't exist in the condensed phase in that form. They're actually tied up in some equilibrium system where they form dimers or trimers or some other complicated structure. And when we do our chemical analysis of it, we use a derivatizing agent, and that derivatizing agent pulls everything back towards the building blocks, basically. And so we can speciate it because we have pulled it back apart, basically. And it was really the more complicated forms that were in the condensed phase out of the tailpipe. So we wanted to test that theory and see whether or not we could recreate those results, get a lot of light carbonyls, find them in the condensed phase again, and then this time look very specifically at whether or not we expect them to evaporate or not under different conditions. And so that's the experiment that we tried to design. Now, that's hard because you're working at very low concentrations. I mean, people make the measurements at 100 micrograms or a few hundred micrograms because it's really easy to measure stuff at that range. You drive it down to 5 or 10 micrograms per cubic meter in a dilution sampler, and now suddenly you're running 30 FTP cycles trying to get enough mass. Nazat remembers this. We just kept going day after day after day trying to get enough mass because we wanted to get it at a realistic dilution factor, but we still needed enough stuff to chemically speciate. So it's detection limit challenges. Those are really challenging experiments to run. But nevertheless, we think that you really want to run your measurements close to where it lives in the atmosphere. You don't want to do some industrial chemistry out of the measurements and then somehow think you know how to project it in the atmosphere. So we really felt strongly we needed to get there. And then we wanted to understand what controls the partitioning. What are the mechanisms? Is it absorption? Is it adsorption? Is it chemistry? Or is it something else? So the experiment that we designed was to try to have a test matrix with 4 boxes. We are going to vary the relative humidity and the black carbon content of the dilution air that we're going to mix into the samples. So before, when we did this, we just clean up the dilution air, make sure it's particle and gas free, mix it with the hot exhaust, get it to close to an ambient concentration and call it good. But now if we want to understand the partitioning, we want to add some black carbon to that dilution air, provide some surface area for these things to adsorb onto and see whether or not we suck more stuff into the condensed phase. Or perturb the humidity of the system and see if somehow it cares about water. The other thing that we were doing is varying the temperature. And so every one of these 4 boxes, we also had multiple temperature measurements at ambient temperature, 25, 50, or 75 above ambient temperature to try to watch how the system behaved to that. And we were hoping that by varying these 3 things sort of in concert, we would get some insight into what was going on with this system and whether or not it's true that all this primary organic aerosol is going to evaporate at ambient conditions. So this is a picture of the dilution sampler setup that we have. Again, the idea is that you want to, in a controlled way, try to mix dilution air with the exhaust to get it to close to ambient concentrations. So we scrub it really well, activated carbon filters and whatnot to get the stuff out. And then in this experiment, again, we're adding stuff back in. We're either adding water or we're adding soot from a flame generator or both simultaneously. And then we'll be trying to perturb the temperature at the same time. And we had a whole host of state-of-the-science equipment measuring what was happening at the tail end of this. We had the traditional denuder filter puff collection measurements, followed by derivatization and GCMS. That's wet chemistry, pretty well established now. We had a high-resolution AMS system measuring this. We had a real-time photoacoustic measurement of the black carbon content of this. We had a real-time chemical ionization mass spectrometer to measure some of the gas phase, just trying to understand what was going on this. So we really went in there throwing the kitchen sink at it, trying to hit it with everything that we could and perturb it in interesting ways and watch what happened. And again, I can't touch on all these results, but I'll try to highlight the important bits for the storyline that I want to develop here. This is just a picture of some of the equipment in action. What you're seeing on the left slide here is the denuder filter puff systems. We use denuders in series to try to make sure that we don't have any breakthrough of that. And then the filter and the puff type measurements. You're seeing the details of the car and the dynamometer then. And then I think in this right panel here, you can see the flame generator. This was inverse laminar flame generator to generate soot. And we were trying to inject, we would have liked to inject about 5 micrograms of soot in there. It turns out we couldn't completely control the system exactly where we wanted it, so we ended up injecting about 15 or 20 micrograms of soot into the system. But that should only make it easier to see an adsorption effect where we're bringing stuff in. And then we had some cascade impactor measurements as well. The left-hand side shows a MOUDI impactor that was collecting samples from the setup. So again, this was an experiment that we had done before, and we focused on low-emission vehicle technology. So these cars were 10 to 11 years old at the time that we ran the experiments. And that actually matches pretty well with the fleet average in the United States. The fleet average, I think, is something like 10 or 11 years old. So we were pretty close to being, I think, relevant and realistic in this. Now, if you go out on a highway or in a tunnel, you're going to see a much broader range of vehicles, and some of those vehicles emit pretty high, and so that can push things around. And I'll get to this in the end in the recommendations. By no means do I think this is the exhaustive end of the study. We need to do more fleet characterization or use other studies to understand that fleet characterization, but this helps us understand some of the chemistry. So the fleet comparison was pretty similar in 2002 when we did this versus 2011, but more miles on the cars. That's one thing that changed. Same technology, but more miles in the intervening 9 years. And then the fuel changed. We still had MTBE in the fuel, I think, back in 2002, and we basically replaced that with ethanol. And you're going to see some of that change the Carbonyl Speciation later on. You can actually see that in the results. So, and I think it makes sense. All right, I've kind of already run through the analytical methods, so I won't belabor that, but we had everything from the traditional to the very, very cutting edge and new, basically. Traditional stuff, not real time, and the cutting edge stuff, real time. Takes a year to invert the data, but you get real time information after you go through that process. All right, so just to put things in context, when you dilute it down to ambient concentrations, 5 micrograms per cubic meter or less, what does the carbon look like being emitted from the tailpipe? So these are size distributions. There's particle diameter on the lower axis, and there's concentration of mass on the vertical axis. The black is the elemental carbon. So it's the carbon, nobody's fighting about that. That's black's carbon that is not volatile, it's not going anywhere, and it is the majority of the carbon in the system at realistic concentrations. If you leave this at 100 or 200 or 300 micrograms, that's a different story. You'll see far more organic carbon per unit of elemental carbon in the system. But if you get it down to something that's atmospherically relevant, it's mostly already, that evaporation process has happened. The question is, does this last little bit evaporate? And that's what we're fighting about, or having a spirited conversation about, I should say. So the measurements from 2002 on the left panel, and then the more recent measurements on the right panel, looking at the base condition, or the condition where we increased the relative humidity, or we adjusted the elemental carbon in the system, or we did both in the lower right-hand panel. And the story largely stays the same in terms of there's not a lot of organic carbon there to start with. The question is, can we push it around at all through these various modifications of the dilutioner? Okay, so the first thing that I want to talk about is vehicle-to-vehicle variability. Cars just don't follow an average. This is a plot of the black carbon emissions rate from the 8 different vehicles that were in our test fleet. It's the vehicle number on the lower axis, and then it's the concentration, the emissions rate of black carbon on the vertical axis, expressed in milligrams of black carbon per kilogram of fuel, I believe. And there is the error bars here, and the median, the box and whisker plot, comes from sort of replicate tests of that vehicle. Or also it might be sort of the variation within a test segment. There's just a lot of variability between the cars. You can't look at a car and say, oh, that's going to be a high-emitting black carbon car or a low-emitting black carbon car. There's just a lot of vehicle-to-vehicle variability. It's only when you start getting into large numbers and you do the averaging that things sort of calm down. So it's hard to look at a few vehicles and sort of get a fleet representative average out of this thing. And that should be a message that I hopefully will consistently say throughout. There are high emitters, and high emitters, you may not be able to pick them out. Even these are not smokers necessarily, but they just emit significantly more than others. The emissions are variable on the test cycle is the second point that I want to make out of this. This is the black carbon emissions in the green here versus the driving trace, the time for the driving trace, and different cars are shown in the different panels here. And what you can see is that there's a lot of variability with where you are in the driving cycle. During the cold start, there's almost always a burst of black carbon emissions when the car is probably running a little bit fuel rich. When you hit the second sort of hard acceleration, there's oftentimes a black carbon emissions there as well when the car is already heated up. So constant speed tests are going to have some issues in representing that variable emissions rate within a test. And so this is not to say that tests that are done at constant speed are useless, but just recognize what they're good for and what they're not good for. Dynamometer tests are hard because you can't get a large fleet in there, and there's a lot of vehicle-to-vehicle variability. But you go out to a roadside or a tunnel or something like that, and you get a lot more vehicles, but they're all driving pretty much the same speed, same time, and is that representative of what you're trying to look at as well? And everything has its strengths and weaknesses, and you should look at the weight of evidence from all the different studies before you try to draw strong conclusions about what's happening. Is I guess the reason that I put this slide up there. The other thing that was really interesting, sort of a gee whiz type of thing with the instrumentation that we had, was looking at the oxygen to carbon ratio in these emissions. So what you've got here are measurements from the AMS, the Aerosol Mass Spectrometer, the high-res instrument. It can make a pretty accurate measurement of the oxygen to carbon ratio in those particles. And what you're looking at is the emissions rate, or the concentration in the tunnel on the lower axis under the conditions that we ran the test, and then the OC to ratio on the vertical axis. What this doesn't tell you is the absolute, well, I guess it does. It shows you the absolute concentrations are highest towards the right. What it shows you is that the oxygen to carbon ratio goes up as you have the vehicles that are emitting less and less. And so one plausible explanation for this is that the vehicles that are emitting more are emitting a lot more motor oil in the system, and that doesn't have a very high oxygen to carbon ratio. And the vehicles that are emitting less are emitting a lot more fuel combustion products, and that might indeed have a much higher oxygen to carbon ratio in it. And so you start to see trends like this that give you some insight into what might be going on. And we're definitely still trying to find all the important points in this data set, but this jumped out as me as something that was very interesting and relevant. Okay, so while we're talking about the AMS, and this is an instrument that has sort of revolutionized our measurements of organic aerosol in the past years. You know, these Van Crevelen plots or various types of plots where you can look at the speciation, look at the real-time concentration with this instrument has really drawn a lot of attention from the field, a lot of publications on this, a lot of effort gone into making these measurements. So I hesitate to say anything that is negative about them, but yet I feel compelled to point out that we didn't have complete agreement between our AMS measurements and the traditional ECOC measurements in our experiment. So what we found was that the AMS consistently measured less primary organic aerosol than what we measured off a traditional ECOC measurement in our system. And this happened at all temperatures that we ran the experiment at, happened at high elemental carbon or high elemental carbon and relative humidity. And we don't fully understand why. We have some clues, but we don't fully understand why. One of the theories that hasn't been shot down yet is that the AMS defines organic carbon as anything that will volatilize after a few seconds at 600 degrees Celsius in their system. It's under vacuum. Anything that doesn't evaporate then is going to be classified as not organic carbon. That's not how the traditional technique works. The traditional technique ramps up the temperature in the ECOC analyzer higher than that, like 800 degrees or something like that, before you bring it back down, and then you add oxygen to the system and try to measure the elemental carbon in the system. So there's a possibility that the AMS is not able to measure what I call the very non-volatile carbon in the system, or not measure all of it in the system. Now, looking at this, the AMS crowd was quick to point out, well, maybe your measurements are wrong. I mean, maybe we're right and you're wrong. And I take that to heart. I mean, I have to consider that possibility. And so we went around and tried to compare everything, cross-check everything that we could. So we had measurements, you might recall with that MOUDI impactor. A MOUDI impactor measures carbon using an aluminum foil substrate to collect the samples. That aluminum foil substrate doesn't have a lot of surface area in it. You know, we're measuring with the quartz fiber filter. That has a tremendous amount of surface area, and you always worry about positive adsorption artifacts of the gas phase vapor onto that. But we were running 2 denuders upstream of our quartz filters, and so in theory, the denuders would have stripped out all the gas phase material, and we wouldn't have to worry about this. What we did then was to try to compare the MOUDI measurements of the organic carbon to the filter-based measurements of the organic carbon to see if they agreed or not. And if they do, then I'm reasonably sure that we don't have a big positive adsorption artifact in our traditional measurements. And what you see on the left-hand side is the summary of the offline techniques where we do just that comparison. And the results look pretty good. You basically see very good agreement between the MOUDI measurements of the organic carbon and the filter-based measurements of the organic carbon, which gives us some confidence at least that we're probably not biased high on the traditional methods. And it probably is that the AMS, for whatever reason, is measuring less organic carbon than us. And you see the real-time measurements on the right-hand side. The AMS is in red, and you can see that negative bias very clearly relative to the traditional methods. There's a lot of AMS measurements going on right now. It's being used as if it's flawless. I think in an ambient sample, where you have a whole bunch of different sources contributing to the ambient sample, it may well be flawless or close to flawless. From this particular source, it looks like it might have some issues. And so that's just a word of caution about how to interpret your results. And there probably can be fixed. Everything can be fixed, but it's just a question that needs to be looked at. All right, so more evidence then, just to show you an ECOC thermogram. This is a measurement of the organic carbon that evolves from a traditional sample as a function of the temperature in the system. Or I guess it's time on the lower axis of these plots, and the temperature ramp is the right-hand side of the scale here. It's the black line in each of these plots. I drew a line that intersects the temperature ramp at 600 degrees Celsius, and I dropped it straight down. So you can see carbon to the left of that line is carbon that the AMS should definitely get. It's lower than 600 degrees is where it evolves. But we've got a lot of carbon to the right of that line in the ECOC thermogram. That's 600 degrees is pretty hot, right? So that's carbon still that's not elemental carbon. I chopped the EC part of this trace off because it's so much higher, it kind of squashes all these results into the axes. So we're not looking at EC anywhere in this plot. This is truly just a plot of the organic carbon. Everything to the right of that is high temperature, higher than 600 degrees Celsius is where it evolves. And we think that this source might emit some of that material. And it's extremely non-volatile. I mean, that gives you sort of a guess of where I'm going with this presentation. There's some really non-volatile carbon that is not going to completely evaporate no matter how much you dilute it in motor vehicle exhaust. All right, so onwards then, talk a little bit about our fleet characterization in the context of other experiments that have been run recently. So Carnegie Mellon, under ARB sponsorship partially, has done work recently looking at motor vehicle emissions and the SOA formation potential for motor vehicle emissions. And they also looked at the primary organic aerosol volatility at the same time while they were there. And so we had a great data set to compare against and try to understand the differences. We actually worked this backwards, but I'll tell it going forward. So, one of the things to understand is, well, how did our fleet compare to their fleet in terms of emissions rates if we want to understand what they measured versus what we measured? So what I'm showing on the left-hand panel here is the Carnegie Mellon fleet of 8 vehicles or 7 vehicles that they did their POA volatility experiments with. And it's the natural, or it's the log 10 emissions rate on the lower axis for the different vehicles. So this is like a distribution of how those vehicles looked. The open bars in the background are results from the Kansas City study. So this is a EPA, US EPA sponsored study out of Kansas City where they had a very large fleet and they characterized the emissions from that very large fleet. And so we were curious of where we stack up on this. What you can see is that half the Carnegie Mellon fleet that they used in this study emitted more than 10 milligrams per mile, which is on the upper end of what US EPA sort of characterized as a national sort of perspective. We actually wrote a test plan where we would not allow a vehicle that emitting more than 10 milligrams per mile into our fleet. So half the vehicles here we would have called high emitters and we would not have allowed into our fleet. Our fleet is characterized on the right-hand side, and you can see it's the same open bars, it's the same Kansas City national fleet on the background, but our vehicles fell into the lower third of that sort of national snapshot. So you might expect then that we're going to get different answers because we started with very different vehicle fleets, and that indeed is going to turn out to be partially true in terms of how we characterize this. All right, so on to some of our results then. So the pictures here are looking at what we call mass fraction remaining after you heat it up. So people use temperature as a surrogate for dilution. If it's semi-volatile and you heat it up, it should evaporate. If it's semi-volatile and you dilute it, it should evaporate. And there's theories that tell you, if you heat it and you get this much evaporation, then this was what it will do if you dilute it. You can sort of understand things out of that measurement. And it's one of the techniques that people use to look at particle volatility. So on the lower axis of each of these plots, you see temperature. We ran some at 25 degrees, the base case temperature, 50 degrees, 75, and 100. And what you're looking at on the vertical axis of every one of these plots is the mass fraction remaining then from our experiments of the primary organic aerosol. Now we did this using AMS data, even though I'd already discussed some of the warts on that, but we used it with AMS data. We used it with the middle plot is the ECOC analyzer, the traditional method. And then we also did it for the Carbonyls, the detailed speciation that we did on some of these, and look how much they partition. And in no case do we see strong evidence of complete evaporation at 100 degrees Celsius. Now this is a little bit misleading. We designed the residence time at that temperature based on previously published results, which turned out to be not very accurate or not very representative of ambient conditions. And so we probably could have benefited from a higher residence time in the hot temperature zone of this experiment. And we're going to have to use the models then to sort of project what would have happened if we would have left it at that hotter temperature for a longer time period. Before we do that, though, I want to look at a little bit of the results as a function of the driving cycle phase. So we also have results from the AMS throughout that driving cycle. The UC driving cycle is about 20 minutes long. It has some cold start and accelerations and so on and so forth. We were using the first couple phases of that. And so we know something about the cold start phase. We know something about the later phases when the vehicle warms up. The middle panel here is the AMS measurement of the organic aerosol mass. A lot more organic aerosol mass coming out in the cold start portion of the driving cycle, and then things sort of settling down, but not zero in the hot running portion. And then you're looking at mass fraction remaining, so at the different temperatures, the 4 different temperatures from those different phases. And what you can see is that the particles look more semi-volatile during the cold start than they do during the hot running portion of the phases. And there's probably some composition changes that explain that. But basically, during the cold start, it looks like those particles are more amenable to evaporating than during the hot running portion of the driving cycle. All right, so we're going to try to model this now. One of our goals was to not just observe it, but to try to put a framework around this for how we can explain it and how we might put it into regional models. So what's the kernel of that? Well, a lot of the community has been trying to describe aerosol volatility with the volatility basis set, basically. You describe a whole series of different particle volatility bins. So some very semi-volatile material, some less volatile material, and so on and so forth, sort of a continuum of possibilities. The material that appears at the far right side of these plots, the C star being very, very high, is very semi-volatile material. It wants to be in the gas phase more than it wants to be in the condensed phase. The things that appear at the left side of this plot at low C star values is very low volatility material. Chris is laughing at me because I made him express this as one over KP for about 3 years, but it's the same thing. So I'm converted now. I'm using C star. So you've got a description then of whatever source that you're looking at. We're going to try to explain our data using not one volatility basis for the primary organic aerosol, but 2, because we think that there are 2 different types of organic carbon being emitted from this vehicle. And it's not hard to guess. Look at the organic carbon going in and think about what it could possibly be. So motor oil, obviously, but then fuel is the other big source of carbon going into the system. I don't think we're converting CO2 to particle phase carbon in the system, so that carbon's got to be coming from someplace, and motor oil and fuel are the only 2 real possibilities. So what we're going to see is that our representation of that volatility distribution involves some very, very low volatility material, which we think is fuel combustion products, and then we have lubricating oil, which has been measured sort of independently. Its volatility basis set has been measured, and this is how we're going to try to explain our data. So when we do that, we get a picture that looks something like this. So this is the different temperatures, again, on the lower part of the plot, and then the mass fraction remaining on the vertical part of the plot. And I'm taking all the vehicles that we tested, and I'm making a box and whisker plot of them at each temperature. So that's what the distribution looks like at each temperature. And we're trying to see how well the model is able to recreate that. The 2 lines are what you would get if you use the Carnegie Mellon sort of representation, a single volatility distribution to represent the results. And depending on the assumptions that you make about the particle surface area, the particle diameter, the resonance time, and blah, 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 you can get either the blue line or the red line. It sort of changes a little bit, but your answer is somewhat in the median there. And you would anticipate then that you could get almost complete evaporation of that material as you go to hot enough temperatures. What we sort of focused on in our reanalysis of this data, our measurements using that Carnegie Mellon single volatility distribution model are on the left. Reanalyzing the Carnegie Mellon data is on the right. You get the same sort of picture out of this. But what we focused on was that model doesn't do a very good job of reproducing the scatter. Yeah, that might explain what the median vehicle does, but there is no median vehicle. We cannot explain the scatter in the data with a model that uses one volatility basis set to describe the POA from tailpipes. And so what we ended up doing is using our 2 volatility basis set, and that worked a lot better. And the easiest way to sort of quantify or describe how much better it worked is just to draw the mass fraction remaining that was observed versus the predicted mass fraction remaining using a 1 distribution model or a 2 distribution model, and look at R squared. How well does it recreate the data? If you use a 1 distribution model, which is shown here on the left-hand side, you get an R squared of about 0.52, which isn't so hot, obviously. If you use that 2 volatility distribution set, you get an R squared of about 0.94, which starts to look a little bit more convincing in terms of what's going on. So you cannot capture the full range of behavior for POA volatility with a one volatility distribution model, basically. And that comes out in the vehicles as well. The interesting bit, why do we get 0.94 and not 1? Well, it turns out that in some of these experiments, as you heat the aerosol up, you actually get more organic carbon in the condensed phase, not less organic carbon in the condensed phase. And that does not jive with absorption theory at all. I mean, those models with the volatility basis set are completely partitioning models. There's no chemistry, there's no formation in there. But in our data and in the Carnegie Mellon data, there's evidence that at mild heating, you're actually seeing more organic carbon in the condensed phase, not less. And that suggests very strongly that there's chemistry going on. You're heating things up, you're speeding up the chemistry of some of the reactions, and you're producing more condensed phase stuff out of that. And we don't get an R squared of 1 because this model doesn't have chemistry in it yet. And that's, the chemistry is that interesting bit. It's what I was saying before about maybe the carbonyls are building blocks, and you're putting them together somehow in that chemical system. All right, so what does it mean then? Well, the interpretation of that, this is for our vehicles, is that a lot of the vehicles are emitting a mixture of fuel and oil, and it's hard to predict ahead of time which ones are predicting more fuel and which ones are predicting more oil. So rather than trying to predict that, I'm just inferring it from how volatile or not volatile their primary organic aerosol looks, and then just put up the figure of how it comes out. So for the 8 different vehicles that we tested here, this is the relative contribution to the primary organic aerosol from either fuel or oil. The oil is dark, and the fuel is the open part. And what we observe out of this, out of our 8 vehicle test fleet, which is not statistically representative of the fleet, but it's something, about half of them were mostly oil, and half of them were mostly fuel. If you average everything, you'll probably get an average vehicle that would almost completely evaporate, left to its own devices in the ambient air. But that isn't how it's put together. It's not an average. It's extremes. Some are mostly fuel and some are mostly oil. And the mostly fuel ones are not going to evaporate under any condition. Or mostly fuel combustion products. I should keep saying that. It's not fuel, it's fuel combustion products. Fuel would be very semi-volatile, but fuel combustion products not so much. And if you use the average or the median, you're going to get the wrong answer, is the big take-home story. You need to recognize that it's 2 separate different things. Now, what the fleet emissions rate looks like for these 2 separate things is an open question. That's one of my recommendations, is people should look at other studies or make more measurements to figure that out. Look at the Carnegie Mellon fleet. Remember, the Carnegie Mellon fleet ran a lot higher. It was orders of magnitude higher. It was above 10 milligrams per mile in that fleet. If you reanalyze their data, it's mostly motor oil. So they were emitting higher because they had higher oil emissions out of their vehicles. So yeah, it looks a lot more semi-volatile because oil is semi-volatile. But I don't know whether that's representative of a fleet or not in California. All right, so just a few more plots then of looking at that. These are just figures showing again, the distribution of oil or fuel emissions from the different vehicles. The UCD fleet is on the top. The Carnegie Mellon fleet is on the bottom. It's, again, the emissions rate or the emissions factors, the logarithm of that on the lower axis. The oil is on the left and the fuel is on the right. And what you can see is that actually the Carnegie Mellon fleet didn't just emit oil at a higher rate than our fleet did, but it actually emitted fuel at a higher rate as well. So orders of magnitude higher emissions out of those vehicles. And is that representative or not of the California fleet is something we should wonder. Okay, so what is this stuff, this fuel combustion product? What is it? And this is where we're getting more and more speculative. But we find these carbonyl building blocks in the condensed phase. And I call them building blocks again because they wouldn't be there natively. You're talking about stuff that's so light, there's no way that under a normal partitioning mechanism it would go into the condensed phase. It's got to be there in some chemically more complex form that we can pull apart when we dump the derivatizing agent into the sample and try to stabilize all of it. We're actually pulling it back through some equilibrium system. Our theory is that chemistry has an irreversible step in it some ways. And once it crosses that step, you can't pull it apart anymore. But anyway, so let's go look at some of those building blocks and try to see how far we can get with that. So this is just a QAQC. Just we measured it twice under similar circumstances. Do we get the same answer? And by large measure, we do. So that builds some confidence. And then we want to look at how much of the organic aerosol is made out of this stuff. Last time, depending on the vehicles that we tested and the drive cycle that we used, we got something between 18 and 30% of the organic carbon back in 2002. This time when we did the same thing and did the same analysis, it's again, significant numbers. So 13 to 40% of the organic aerosol that we measured on that filter, we believe, is composed of these carbonyl building blocks. So that's pretty significant. The speciation changed a little bit this time, though. The upper plot shows the 2002 measurements, and you've got the aliphatic aldehydes being the biggest single category here in the polka dots, and then dicarbonyls being number 2, being the second biggest category. When we back in 2011, again, the aliphatic aldehydes were sort of dominant in what we could characterize, and under all conditions, the base case, or the high relative humidity, or the high EC, or the high EC plus relative humidity. But number 2, the sort of second runner-up, changed. Instead of being these dicarbonyls, it was aromatic aldehydes now, coming in number 2. And so why did that happen? Well, the vehicles got older, which definitely could matter, but the fuel changed, and I think that maybe is the more important story here. And so NAZOT helped me run this down, the fuel composition data from the refineries for the past decade or so. We got that access from ARB Fuels folks, and we were able to line it up with this data, and it tells a little bit of an interesting story. So if you look at, let's start with the total aromatics here in the left-hand panel. The fuel, this is the 2002 in the first 2 bars, and then 2011 in the second 2 bars. And the fuel is the first measurement here, and this is just a box and whisker plot of all the refinery data in California. And the aromatic content went up slightly between 2002 and 2011. Now, slightly, obviously those error bars overlap, but the median did go up, and the extremes are higher in 2011. The particle phase aromatic content, the aromatic aldehydes, jumped considerably more than the fuel did. It went way up. So, that total aromatic content has benzene, has a whole bunch of other things in it, although we don't use as much benzene now, right? It's not as much benzene, but it has a whole bunch of stuff in it. Maybe all that stuff isn't what makes these aromatic aldehydes. Maybe it's only a subfraction of that, and so you see the magnification in the condensed phase aromatic aldehydes. I don't know. We don't have enough data to know for sure, but it's interesting. The other thing that we looked at then was the MTBE shift to the ethanol shift, basically, and we think that that's driving some of this as well. So the dicarbonyls going away, and the aromatic aldehydes sort of becoming the second largest fraction of the aldehydes here. So it's interesting. Now, does this have health effects? I don't know. I don't know what the health effects are of any of this stuff, but the composition changed, and that's not just composition that a few of us breathe. It's composition that all of us breathe. We all take a walk at night with your kids beside a road. And so everybody, we just ran a pretty big experiment when we jumped from MTBE to ethanol that maybe we didn't realize that we run. You change the composition of the fuel, you're changing the detailed chemistry of the particles that people are breathing. And I do not know what the implications of that are for health. All right, so what did we measure? Measured a lot of, like I said, light aliphatic stuff. So propanol, little building blocks that would never in a million years partition there by absorption theory. We're measuring high concentrations of those in the condensed phase. And so we're pretty sure that it doesn't exist as propanol or these other light compounds in that phase, and that it is tied up in some more dimers, trimers, whatever you're putting together in the condensed phase out of these building blocks, and that our chemistry is just pulling it apart when we derivatize it, until you cross that irreversible step, at which point it looks like it's very low volatility and you can't pull it apart anymore. All right, so the interesting bit then, I haven't talked very much about the effects of our different experimental conditions. So it turns out that humidity pushes the answer around. If you look at the different things that we varied the relative humidity, we varied the elemental carbon, we varied the elemental carbon plus relative humidity, and if you look at the results across the board, the thing that jumps out at you sort of well above the base case bar is that humidity matters. And what that suggests is that there's some sort of aqueous chemistry going on that is influencing the production of these carbonyls. You add more water to the system, provide more reaction volume, and you end up producing more total gas plus particle phase stuff of this. When we added the elemental carbon, what we started to see was evidence that maybe we're scavenging some of the precursors out of the system. So, one of the theories going into this was maybe the elemental carbon, the black carbon, would provide more surface area, and you'd get more compounds going into the condensed phase. At least for the ones that we're detecting here in these carbonyls, that didn't look like it happened. It looked more like what you're seeing is that the black carbon surface area is soaking up the precursors for that chemistry and shutting down the chemistry. Now, we, again, remember, instead of being able to dump 5 micrograms in under controlled conditions, we dumped 15 or 20 micrograms in. So we kind of flooded it with black carbon. And I don't know whether it would still dominate at the lower 5 microgram level, but it seems like that's a plausible explanation to explain the trends that we see in our data. All right, so you're seeing also the Carbonyl speciation change a little bit under the different conditions, the high relative humidity, or the add the black carbon, or add the black carbon and increase the relative humidity. Not dramatically, though. Under no case do we ever see the aliphatic aldehydes not sort of dominating the signal. But we do see certain things appear above detection limits that weren't there when we start manipulating some of these experimental conditions. We're still staring at this data, trying to fully understand it. The project ends for ARB, but we sit there and stew on it for another couple of years, and still, papers will still appear. So it's going to take us a little bit longer, I think, to wrap our heads completely around what all of this means. But we observe that the experimental conditions matter. This system is not chemically inert. All that we're doing, this is at the end of the tailpipe, we're mixing dilution air with it. The chemistry is not frozen. It's not just partitioning that's happening. There's active chemistry going on. You change the conditions, you change the chemistry. And I think that's very clear from these measurements. And I'll gloss over that just to get to the next phase then. So the real-time gas phase measurements were kind of interesting because they could measure the cousins of things that we were measuring in the condensed phase. And so I said propanol was a big hitter in terms of the carbonyls that we observed in the condensed phase. Well, it turns out if you continue reacting propanol, you get propionic acid. You make the acid form out of the carbonyl. And we could measure that with the real-time, the SIMS, the chemical ionization mass spectrometer. And so what you're looking at in this figure is a time trace during one of the drive cycles of propionic acid, which is in the black here on the left-hand side, and as a function of the driving trace. And what you can see along with it is the concentration of NOx in the system as well. And they're almost dead spot on in terms of the time trace. And so clearly the chemistry that forms propionic acid is somehow related to the NOx concentrations in the system as well. We think it's kind of interesting then to think about that in relationship to what's going on with all these light carbonyls that we're seeing in the condensed phase. The propionic acid wasn't the only thing that was measured. We measured a whole range of different acids, and what we did to try to characterize that was to try to look at their emissions factor as a function of the carbon chain length that's in the acid. So you can see on the lower axis here carbon chain lengths of 2, 3, up through 10 carbons in that acid. And then you've got the, this is organic acid, not organic aerosol now. I apologize for that. Didn't catch it early enough to fix it, but I want to point it out specifically. So these are organic acid emissions factors expressed in milligrams per kilogram of fuel burned. And you can see that the lighter acids are emitted in much higher concentrations than the heavier acids are, the ones with more carbons in them, basically. And that reflects, again, the chemistry that's going on. And then we also expressed it as organic acid concentration per CO concentration in the whole system. So really the online techniques, the new techniques are really powerful. I mean, who could have ever imagined doing this with traditional wet chemistry? There's really nifty things that come out of it. But you shouldn't skip over the step of comparing it to the traditional techniques or gloss over the problems when they happen. And I think the AMS is teaching us that yeah, it's great, it's a gee whiz instrument, but really look at it skeptically until you understand the strong points and the weak points of it. But there's clearly tremendous stuff that you can do with these measurements. Okay, so what about the effect of the temperature? If things were partitioning really strongly, as we heat the sample up, then you would expect to see a lot more of this go into the gas phase now. We're looking at the gas phase. And so can we detect that signal? And the answer is maybe, but not quite. So again, these are acid partitioning measurements now. I've broken them out, 4 panels, the C1, the C2, or no, so C1, C3, C4, and C5 acids in the different 4 quadrants of this. Temperature now is what's varying here. And you can kind of see a little bit of an increase at the hotter temperatures, but not a tremendously strong signal. It's nothing that's out of the error bars, certainly, of the measurement. So not strong evidence of a massive partitioning phenomena happening there as well. Okay, and then just one more kind of neat thing that's completely unrelated to what we're talking about, aerosol volatility, but the isocyanic acid emissions from the vehicles were something that could be measured, HNCO, something that's of some health concern, and this technique does a very admirable job of measuring that. And so I think you'll be able to get pretty rock solid emissions factors from motor vehicles from this. And diesel vehicles emit this as well as ships, and Tim's group did a pretty good job of trying to look at all those things. We measured 1 diesel vehicle in the study, but we didn't measure any heavy-duty diesel vehicles, but there's literature values available for those. So just gives you an idea of what's going on. And the chemistry of this can even be understood as well. Tim had a nice chemical mechanism to explain how it forms. The catalyst has to be hot. If you go back and up and look at this, everything that I've showed you so far tends to be emitted more in the cold start portion of the test at the left-hand side of the time traces. Here we're looking at something that only gets emitted after the catalyst reaches operating temperature. And it's because of the chemical mechanism that you take to make it. It can be understood and modeled and explained, basically. All right, and that just shows you the sort of the dependence of the HNCO production on the CO and the NOx mixing ratios. The idea is that when you have a lot of CO and NOx, you're going to make more of this stuff, and when you have not very much of it, you're going to make less of it, and again, because of the chemical mechanism. All right, so what conclusions do I want to try to draw from all this? Well, we think that POA for motor vehicles is not one thing. We think it's 2 things. We think one of those things looks a lot like motor oil, behaves like motor oil, and is pretty semi-volatile. It will evaporate. But the other thing is not semi-volatile at all. It's very non-volatile. We think it's a fuel combustion product. We suspect it's made out of carbonyl building blocks. That's a little bit up in the air yet. But it's not going to evaporate. And we should expect that in our model simulations, basically. We're going to have to build a statistical distribution from this, either through tunnel studies or some other techniques, characterizing a bigger fleet of vehicles using these temperature volatility techniques to understand it and what the fleet looks like. Our preliminary look at 8, what we think is representative vehicles, suggested 50%, but that's pretty wide error bars on that. I would believe 60, I would believe even 80. I probably wouldn't believe 99. But there's a lot of variability in there, but I think we know enough now to know what to look for when we go back to characterize the fleet. The chemistry in the system is active. You change the relative humidity, and you're going to change the carbonyls in the exhaust. So the chemistry is still ongoing, and I think that needs to be recognized. It's not just partitioning. There's active chemistry happening in the exhaust of the vehicles. This wasn't a smog chamber experiment. We didn't add any oxidant or anything like that. This is just what was natively in there. All we added was the water vapor. And it looks like the increased surface area of adding black carbon to the dilution air did not enhance the POA emissions. And in fact, if anything, it suppressed it because it looks like it scavenged gas phase precursors. We don't see a significant enhancement. So adsorption on EC is not explaining the POA formation. It's some sort of chemistry that's happening. And just the normal what happens to motor oil. So what are the implications of that for modeling? I'm looking at Adjit when I say that. Well, actually, I got to look at the whole back corner there. So if you went in with a median volatility distribution, one volatility distribution to explain what's going on, it's probably going to be semi-volatile enough to evaporate completely, and you would predict no POA in your model. If you go in with 2, the motor oil part of it is going to evaporate, but the fuel part of it is not, and it will not go anywhere. So we think it's really important. This has implications that need to be recognized in regional modeling. The other thing that I wanted to try to have a little bit of food for thought on is, there was a lot of SOA measurements made by the Carnegie Mellon Group the last time that they were down there. And these were some of the vehicles that they measured. Not all of them. They measured a lot more vehicles, but these were some of the vehicles that they measured. I'm submitting that the POA emissions rate from these vehicles are not very representative of the California fleet. I put it to you, how representative are the SOA formation measurements from those vehicles? And how do you interpret those? And so, as I said, Carnegie Mellon measured a lot more vehicles than this, and they have individual data from individual experiments. But I think you might want to be cognizant of the emissions rates of the vehicles when you look at that data and decide what you want to put into your analysis. Because I don't think that every vehicle that they measured those SOA emissions rates for are truly representative. If Alan's watching this on the internet, he might just roast me on this, I don't know. But I believe that's honestly a fair observation, that those vehicles that are emitting more than 10 milligrams per mile maybe are representative of the California fleet or maybe not. I don't know. But it's going to matter for primary, and it's probably going to matter for secondary as well. I don't think that you will get the same amount of SOA formation out of those vehicles as you would with others. All right, so my recommendations based on all this then, we need to characterize a larger fleet, whether it happens with tunnel studies or whether it happens with more dyno studies or both to try to build a weight of evidence. We need to characterize more vehicle emissions. We probably should try to explore the chemistry a little bit more to understand how those carbonyls are there, why they're there, and are they truly related to this non-volatile organic aerosol formation, and how does that chemistry work? What is that irreversible step? The AMS measurement of POA from motor vehicles at least looks like maybe it has some issues measuring the high volatility, what the traditional community calls organic carbon. Maybe we should just redefine organic carbon to be whatever the AMS measures. I don't know. But there's a difference, and it's important to recognize that there's a difference. And we definitely need to have a clearer understanding of that if you want to interpret AMS measurements in the future. So with that, I will end. I think I hit an hour more or less, and happy to answer any questions.
So I'm interested in high RH. You obviously have more water in the gas phase, but I don't think those particles are going to be very hygroscopic. So would you expect more particulate phase water necessarily?
Yeah, so there was sulfate in these emissions.
Okay.
It wasn't emitted all the time, but there were bursts of sulfate, and the AMS can see the timing of that. And it's really interesting to look at the timing of a burst of sulfate, and then there's a timing of a burst of organic aerosol around that as well.
Oh, really?
And we don't fully understand, we haven't fully come to grips with the full implications of that.
So the follow-up then is, if you can add soot, could you just add Delaquest ammonium sulfate to? Would that be feasible in this kind of experiment?
Absolutely, that would be easy to do. But we had a fun time doing this. I don't know if you heard the stories, but we got down there and the dynamometer is on the common electrical circuit down there, and it throws out all kinds of crazy electrical interference. And so you plug the AMS in, and they don't even want a cell phone. They don't even want you using a cell phone around their instrument, right? And so you plug it into this system that's just being churned by the dyno. And so we had quite a time getting things going. So we didn't do everything down there that we could have done, but we just ran out of time, and we got the core of it done, so we called it good. But yeah, definitely somebody could go into that same setup and add ammonium sulfate instead of black carbon and watch what happened. That would be a great experiment to run.
Mike, thanks for a really comprehensive talk, but I'm having a little trouble getting my head wrapped around the implications of this. So you talked about, your 2VD model for regional models. What do you think would be the implications on PM 2.5 estimates?
So we're going to have a chat about this next week. We have done a decade of modeling for California every day, full shot through. Organic aerosol was a big part of that evaluation. We were using EPA's model for that with primary organic aerosol, non-volatile basically. So assuming that we are using emissions from motor vehicles that are in low enough concentration so that they shouldn't be that biased anymore. We get monthly means that actually look pretty good compared to the measurements. If we put in semi-volatile primary organic aerosol that is based on a one volatility distribution set, we will destroy that agreement. All that material will evaporate, or 75% of that material will evaporate. And so the implications are that if you truly want to call primary organic aerosol semi-volatile and start representing that, some things that coincidentally are working are going to stop working very, very quickly. And we're going to have to come up with a secondary organic aerosol mechanism that puts the stuff back. Now, is it right or is it wrong? I don't know. I mean, definitely the models right now do not predict the buildup of oxygen in the organic aerosol correctly. It's very clear that that happens based on AMS measurements. Whether it happens, though, in the gas phase or in the condensed phase is a really good question. And there's 5 different models now for how to do that in either the condensed phase or the gas phase, or more than 5. Everybody's got their model, and they're not like they build on each other. Everybody's trying to jump to tune their model to get the right answer based on their model and only their model. So I guess the short story is, if you went to a one volatility distribution representation of the primary organic aerosol, you're probably going to underpredict POA, and you're going to have to put it back with one of these other models for what's going on. And the chemistry of that is just not understood right now. I don't think there's a clear winner on that. But I'm suspicious of coincidence, and I find it very strange that coincidentally, if we consider the primary organic aerosol to be non-volatile, we get about the right organic aerosol across 10 years of predictions.
In terms of concentration, though, are we talking about 1 or 2 micrograms per cubic meter on an annual average, or something less than that?
In terms of the concentration of the organic aerosol measurements or the model predictions?
The POA contribution.
The POA contribution is 75 or 80% of what we predict for organic aerosol right now. The current models for California don't predict a lot of organic aerosol. The current models for SOA formation are largely biogenically driven, which matters a lot for the East Coast, but matters a lot less for California. We understand what those biogenics are doing in terms of SOA formation really well, or a lot better, but California doesn't seem to be driven by that. We probably measure, or we probably predict about 20 or 30% SOA, and then the rest of it POA right now in our model predictions. And coincidentally, it just happens to work. So if we make it semi-volatile, we coincidentally just have to put that stuff right back in through some other mechanism. And I'm not a strong believer in coincidence. So that explains my bias in the whole game, I guess.
All right, we have a few questions from the web.
Okay, I'll read them. Okay. All right, this is from Dean Atkinson. So Mike was talking about the low bias of the AMS for OC. Is in the OC-EC measurement, charring was a problem solved partially by the optical correction. Anybody thinking about whether charring at the volatilizer could be robbing OC from the AMS? So the question is whether or not there's a charring artifact. You deposit the organic carbon on the AMS filament or plate or whatever, and somehow you char that and it doesn't come back off. I guess it's possible. I don't know the AMS well enough. My observation, though, from motor vehicles, there's not a lot of charring that happens in motor vehicles. There's almost zero correction in the traditional ECOC measurement for charring from motor vehicle exhaust. It's a very large correction when it comes to wood smoke and other things that have carbohydrates and other sugars in them. But there's just not a lot. There's basically zero. So that could be in play here, but I don't think it's in play for this experiment, would be my thought. All right, so, and this one is from Young Yu from CARB. So I have a few questions. How is the AMS response to organosulfates, which might be a part of the OA? Okay, so I don't know yet. I guess Chi Zhang and her postdoc Sonia are still, I think, working on the inversion of the AMS data. It gets presented at conferences as if it's an easy measurement. It's not an easy measurement. I mean, to make an organic aerosol measurement with an AMS, you need a PhD, basically, with somebody who knows how to do this. There's a very involved process in doing this. Whole papers out of those 8 papers that I put up were written on how to do this for the motor vehicles. And so it's not trivial. I don't know the answer to the question, but certainly Chi Zhang would be the person to ask about the organosulfates. So the second question here, could you please explain how to determine the motor oil and fuel contributions to OA in detail? And so what we did was we looked at the mass fraction remaining in the samples at the different temperatures, and we tried to use that model that had a motor oil distribution and a organic aerosol distribution, and all we did was okay, how much motor oil do we need and how much of fuel combustion products do we need in order to best explain the mass fraction remaining. So it was a fitting procedure at that point. Our estimate of how much motor oil versus how much POA from fuel combustion products is completely a fit based on those two distributions. In the past, we've done it with tracers. So in the past, we've done it with the Hopane styrene fingerprints and the heavy PAHs for the fuel combustion products. And I meant to look at how much that slide predicted from the 2002 study of how much we predicted back then, but I believe it was similar. There was some appreciable amount of fuel and there was some appreciable amount of oil in that. So we've done it independently in the past, but in this particular project, it was completely just derived on fitting the volatility that you observed, the mass fraction that we observed. All right, so the third question. I agree with your point about on the dimer or polymer format of carbonyl and OA, especially for lower pH condition. Do you conduct any pH study for the POA? And no, we didn't measure pH, nor did we try to manipulate the pH in our system to somehow test whether or not you get more of this formation under high pH or low pH. I think there's acid catalyzed and base catalyzed routes to the dimer, trimer, sort of oligomer formation. So if you get too far in either extreme, you can drive the chemistry a lot faster. I have no idea what the pH was in our system. But if we go back, or if you go back and measure it again, then I would suggest you measure it. So on page 42, as I understand, the emissions rate for this duty cycle is the average values in the plot, not the integrated values for the whole cycle. And what's the duty cycle? So this is for 42. Let me try to find 42 to make sure I understand this one. So this is a plot, time since engine start. So this is the actual UC cycle, the cycle that we were driving. So it's not an average. This is the actual time trace. So I'm not sure I understand the question, but this slide 42 here it's time since engine start in seconds. So it's looking at the time evolution during the UC driving cycle. So the car speed is going up and down, sort of all over the place. And what you observe then is that you get the highest formation rate after the catalyst gets hot. Because it's reaction chemistry on the catalyst that's actually driving the formation of this stuff. All right.